Welcome back to the deep dive. Today, we are doing something that feels, well, honestly, it feels a little bit like heresy.
It does, doesn't it?
Yeah,
In the world of science, there are certain pillars you just don't touch.
right.
They're load-bearing walls,
Mm.
and you don't go swinging a sledgehammer at them unless you are very, very confident.
And the biggest load-bearing wall of them all is, of course, Albert Einstein. Specifically, special relativity,
hmm
the stuff we've all accepted as gospel, that time slows down when you move fast, that objects physically shrink, that the universe itself is sort of rubbery.
Right, the textbook physics.
Yeah.
It's mind-bending, but we accept it because, well, it's Einstein.
Right.
But today's source material is asking us to just pause for a second.
Yeah.
It's suggesting that maybe, just maybe, we've been looking at the math completely upside down.
It's a radical reinterpretation. We're going to look at a source that argues much of what we call relativity isn't a physical warping of the universe at all, but a trick of perspective.
A geometric illusion.
Exactly. And to see that illusion, we have to go back, way back before Einstein.
We have to revisit the 19th century. A physicist named James Clerk Maxwell and an astronomer royal named James Bradley.
It's a detective story, really. We're going to reconstruct a crime scene using light rays. So buckle up. We are about to challenge the shape of now.
I love that phrasing, the shape of now, because that is exactly what is at stake here.
Okay, so let's set the stage. Usually when we talk about relativity, we start in a void. Just an observer floating in nothingness. There's no ground, no up, just relative motion.
Right. But this source insists we start somewhere solid.
And that's a big deal.
Yes, this is the first major departure. The source grounds us in what it calls Maxwell's absolute space.
Absolute is kind of a dirty word in modern physics, isn't it?
It really is, yeah. Modern physics says everything is relative, there is no background grid. But for this deep dive, the source asks us to imagine that grid exists.
Like a stage.
A giant, invisible, 3D Cartesian coordinate system. This is Maxwell's electromagnetic field. It's stationary. It's the stage where the play happens.
Okay, so we have a fixed stage. Now we need a prop. And the source gives us a very specific setup to visualize.
It's a geometry problem. So picture a flat disk.
Mm.
It represents a Michelson interferometer, that famous instrument used to measure the speed of light.
But for our mind's eye, let's just picture a rigid, flat disk.
Right, a disk with a radius of 10 units. And it's sitting flat on the ground floor of our graph at z equals 0.
And around the edge of this disk, we have 360 mirrors.
Like a disco ball, but flat.
I like that, okay.
Exactly. Now, here is the kicker. This whole apparatus, the disk, the mirrors, the center, it's moving. It's sliding along the ground, the x-axis, at a very specific speed.
And that speed is 0.1 c,
10% of the speed of light.
which is, what, about 18,600 miles per second?
Yeah, so this isn't a casual stroll. It's moving fast enough that relativistic effects should kick in, according to the standard model.
Okay, so we have this flying saucer zipping along the ground. Now, normally, in a physics class, the teacher would say, imagine you are standing on the saucer.
Correct. That's the relative perspective. Einstein would ask, what does the pilot see?
Hmm.
But this source says, no, stop. Don't get on the saucer.
Why not?
Because if you're on the saucer, you're biased. You're part of the system. The source argues that to understand the true geometry of light, we need to step back.
Way back.
Way back. We need to place a camera eye high above the action.
High above. The source specifies the coordinates, right? Z equals 100.
So if the disk is on the floor at z equals 0, our camera is hovering 100 units straight up in the air. We are the objective observers looking down, anchored in that absolute Maxwellian space.
And this camera does one thing. It takes a picture.
A single snapshot. Click. At exactly time t equals 0.
This seems simple enough. We freeze the moment. We see the disk. So what's the controversy?
The controversy, and this is where this source starts throwing rocks at Einstein, is when we ask, how did the image of that disk get to the camera?
Well, light traveled from the mirrors up to the lens.
But how did it travel? This is where the source introduces a concept it calls enslaved light.
Enslaved light. That is a very charged term for physics.
It is, but it's a powerful metaphor for how Einstein treats light in local frames. Think about the classic light clock on a train. You've probably seen this diagram.
Sure.
You have a mirror on the floor of a train car and a mirror on the ceiling. A pulse of light bounces up and down.
Right. And the standard story goes, if I'm on the train, I see the light go straight up and straight down. A vertical line.
Exactly. Einstein's postulate says that inside your inertial frame, the laws of physics are normal.
Yeah.
The light acts as if the train is stationary.
It's enslaved.
It is enslaved to the train's reference frame. It shares the train's lateral motion perfectly.
So effectively, even though the train is rushing forward at 100 miles per hour, the light beam is somehow carrying that forward momentum with it so it stays perfectly aligned.
That's the implication. Einstein says the observer on the train must see vertical motion. But our source today says that is a physical absurdity
Why?
because light isn't a tennis ball. If you toss a tennis ball on a train, yeah, it carries your momentum. But light is a wave traveling through a medium Maxwell's field. It doesn't care about your train.
And this is where James Bradley comes in.
Yes. Bradley is the star witness for the prosecution here. He was an astronomer royal back in the 1700s, and he discovered stellar aberration.
I remember looking at the notes on this. It used the rain and tube analogy. This is really helpful for visualizing it.
It's the best way to understand it. Imagine you're standing in a rainstorm. The rain is falling straight down vertically.
Okay.
You have a long, hollow tube, like a telescope tube, and you want the raindrops to fall all the way to the bottom without hitting the sides.
If I'm standing still, I just hold the tube straight up. Easy.
But what if you start running?
If I run,
Yeah.
I have to tilt the tube forward. Because if I keep it straight up, the back of the tube will run into the raindrops as they fall. I have to angle it so that my forward motion matches the rain's downward speed. I have to create a diagonal path for it.
Precisely, that is aberration.
Yeah.
Bradley realized that because Earth is moving around the sun at 67,000 miles per hour, we are running through the starlight.
Right.
We can't point our telescope straight at a star.
Yeah.
We have to tilt them slightly forward to catch the light.
So the telescope has to aim at where the light is coming from relative to our motion, not where the star actually is.
Right. And here is the crucial point the source makes. Bradley proved that light is independent. It's like the rain. The rain doesn't know you're running. It doesn't magically start falling diagonally just to make it easier for you.
You have to adjust to it.
You have to adjust to it.
Okay, I see where this is going. If we go back to Einstein's train.
The source argues that Einstein ignores Bradley. By saying the light goes straight up and down for the passenger, Einstein is essentially claiming the rain starts falling sideways just because you're running.
He's enslaving the light.
He's enslaving the light to the train.
But wait, doesn't Einstein account for this? I mean, relativity is complex.
Well, standard relativity accounts for it by manipulating time and space. It says, to make the light look straight, time must slow down and space must contract.
But the source argues that this is a huge overcomplication.
It says, no, space doesn't shrink. The light just travels diagonally in absolute space, period.
It's Occam's razor, and Einstein adds warping space and time. The source says, just tilt the telescope.
Exactly. So let's bring this back to our experiment. We have the flying disk at z equals 0, moving at 10% light speed. We have our camera at z equals 100.
The camera takes a picture. Now, we have to do the deep dive calculation. We have to reverse engineer what happened.
This is the detective work.
Yes, we have the photo at c equals 0, but that photo is composed of light rays that traveled from the disk to the camera, and that travel took time.
Right. Since the camera is 100 units away and light has a finite speed, the light we see at t equals 0 must have left the disk earlier. It takes time for the signal to climb that height.
And during that split second, while the light was climbing, the disk was still moving.
It was sliding along the x-axis.
So if we want to know the truth, we can't just assume the disk is where we see it. We have to calculate backwards. We take the angle the light came in, the aberration angle, and we trace it back to the source.
It's like ballistics. If a bullet hits a wall, you calculate the trajectory to find where the shooter was standing when they fired, not where they are now.
And when you do this, when you mathematically strip away the assumptions and just trace the light paths through Maxwell's absolute grid, you find something that breaks the standard model.
What you find is the core of this entire argument. You find that the shape of time for the moving disk is not what we think.
Okay, explain that. Because if I'm on the disk, I think everything is happening now. All the mirrors are reflecting now.
That's your intuition. You assume your now is a flat plane, a horizontal line on a graph where t equals 0 for everyone on the disk.
Right, simultaneity.
But the source says, when you reconstruct the data from the z equals 100 camera, applying Bradley's rules, that flat plane, it breaks. The now for the moving apparatus isn't flat.
It's
slanted.
slanted.
Think of it like a ramp. The source calculates the emission times for all those mirrors on the rim, and it turns out to create that single coherent image at the camera at t equals 0, The light didn't leave all the mirrors at the same instant.
So give me the numbers. I mean, how big is this time gap?
The source finds that the emission times range from t equals negative 0.9
Okay.
all the way to t equals positive 1.1.
Whoa. Wait, so parts of the disk sent their light almost a full second in the past,
Yeah.
relatively speaking, and other parts sent their light from the future.
Well, future relative to the center, yeah. It means that what looks like a single moment to the camera is actually a smear across time. The rear of the moving disk, the trailing edge, is lagging behind in time, and the front of the disk, the leading edge, is ahead.
So the now plane is tilted.
It is a slanted plane. The source describes this as cutting a light cone obliquely. Imagine taking an ice cream cone and slicing it at a sharp angle. You don't get a circle, you get an ellipse.
I'm trying to wrap my head around what this means for the person on the disk.
It means they are living in an illusion. They think all their clocks are striking noon at the same time. But relative to the absolute universe, their noon is staggered. They are riding a time gradient.
It's like imagine walking up a hill but believing you're walking on flat ground. You're actually changing elevation, changing time with every step, but your internal map says flat.
That's a fantastic analogy.
Yeah.
You are physically traversing a slope in the temporal landscape, but your perception flattens it out.
You think you're sharing a moment with the person across the table, but on this slanted plane, one of you is slightly in the past and the other is slightly in the future.
That's it. And this leads to the biggest claim in the source material, the thing that usually melts people's brains in relativity: Lorentz contraction.
Ah, yes. The idea that objects physically get shorter when they move fast.
Yeah. In standard physics, if a spaceship flies past me at near light speed, I measure it as being shorter, physically squashed.
Like an accordion.
And standard relativity says space itself is contracting. The atoms get closer together in your frame of reference.
Which has always sounded, well, magical. Does the metal compress? Do the molecular bonds shrink? It implies a physical crushing.
It's a huge philosophical headache.
Yeah.
But our source today offers a get-out-of-jail-free card.
Which is?
It says, no, there's no shrinking,
You're shrinking at all.
no physical contraction. The disk remains a perfect circle, rigid, unchanged.
Then why does it look squashed? Why do the measurements say it's shorter?
Because of the slanted plane. Think about it. If you are looking at an object, but you are seeing the back part from 0.9 seconds ago and the front part from 1.1 seconds in the future, you aren't seeing the object as it is. You are seeing a time-distorted cross-section.
It's a scanning error.
Exactly. The source compares it to a rolling shutter effect. You know when you take a photo of a spinning propeller with a digital camera?
And the propeller blades look totally detached and warped, like boomerangs floating in the air.
Right. The propeller isn't actually warped, but the camera sensor scanned the image from top to bottom while the blade was moving. The time delay in the recording process created a geometric distortion.
So this source is arguing that relativity, all that stuff about shrinking spaceships, is just a cosmic rolling shutter effect.
That is the argument. Because light has a finite speed, we can never see a moving object all at once. We scan it across that slanted time plane. The object looks shorter, but it's just an optical artifact of the signal delay.
That is weirdly relieving.
It feels cleaner, doesn't it?
It makes the universe feel solid again. It's not that reality is warping, it's that our view of reality is skewed by the information lag.
It shifts physics from metaphysics back to mechanics. Instead of saying space is flexible, we say measurement is tricky.
But I have to play devil's advocate here. Standard relativity works. GPS satellites, particle accelerators, they use Einstein's math every day. If this source is saying Einstein is head-heavy and wrong, why does the GPS still work?
That's the million-dollar question. And the source actually addresses this, though somewhat implicitly. The math of the slanted plane and the math of Einstein's time dilation often produce the exact same numbers.
They get to the same answer.
Often, yes. Einstein predicts you will measure the object as shorter. This source predicts you will measure the object as shorter. Einstein says it's because space shrank. This source says it's because you're looking at a slanted time slice.
So practically the outcome is the same.
Experimentally, they can be very hard to tell apart. But conceptually, they're worlds apart. One universe is a malleable, rubbery manifold. The other is a rigid, absolute stage where light just plays tricks on our eyes.
And that distinction matters. It changes how we understand our place in the cosmos. It shifts the philosophy of what real means.
It also really vindicates James Bradley.
The rain tube guy.
In most textbooks, he's a footnote. Oh, he found aberration in 1727. But this source elevates him to the guy who actually had the physical proof that Einstein ignored.
Right.
It puts the physics back in physics. It says, don't tell me what should happen in a thought experiment. Look at the data.
It is amazing how a simple shift in perspective, literally moving the camera from the train to z equals 100, changes the entire narrative.
It reminds us that science isn't just a collection of facts. It's a collection of models, maps,
Mhm.
and sometimes you need to check if you're holding the map upside down.
Or if you're looking at the map through a rolling shutter.
Exactly. And this reverse engineering approach, calculating backward from the signal received, is actually a very robust way to do science. It forces you to acknowledge the limitations of your sensors.
So let's zoom out. What does this mean for us, for the listener driving to work right now, moving at 60 miles per hour?
I think it highlights the profound, inescapable nature of delay.
Mm-hmm.
We tend to think that what we see is what is happening right now. But whether it's light from a star, or a text message from a friend, or even the sound of my voice reaching your ear, there is always a lag.
We are never truly in the present.
We are always reconstructing reality from signals that are essentially from the past. We're always reverse engineering the crime scene.
And this source adds a layer to that. It suggests that depending on how fast we're moving, literally or metaphorically, our present might be tilted relative to everyone else's.
It creates a unique geometry for every observer. Your now is not my now, not because magic is happening, but because we are viewing the absolute stage from different angles of time.
It's almost poetic. The faster you go, the steeper the slope.
And if you go fast enough, the difference between the front of your now and the back of your now becomes enormous. You are stretched across history.
I want to leave the listener with a thought to mull over. We talked about how this slanted plane means that for a moving object, the back is in the past and the front is in the future.
Relative to the absolute space, yes.
If that's true. If our perception of now is just a slanted slice entirely dependent on our speed, are we ever really sharing the same moment with anyone else? Or are we all just sliding along our own tilted planes of time, intersecting for a brief second but never truly aligned?
That is a haunting thought. But maybe that intersection is all we get.
Thanks for listening to The Deep Dive. Keep looking up and maybe check your angles.
See you next time.